Computational load is the amount of demand that is being placed on a computer system. Load can take the form of memory and CPU and network bandwidth or disk space and other finite resources. When we design systems, we need to prepare for high load events. On a social network, people are much more active in the mornings. On an e-commerce site, Black Friday causes many more users to come online for discount shopping. Distributed applications must be able to scale in response to these spikes in traffic. Cloud computing has changed the popular software architecture patterns, and load balancing has changed along with those architectural pattern changes. With on-demand infinite infrastructure, we don't need to worry about ordering servers and provisioning. And with infrastructure as code, it becomes simpler to manage lots of deployable units. So we can break up our monolith into microservices and have hundreds or thousands of virtual machines or containers running. Enterprises that were started before cloud computing have large on-premise server deployments. But today, many of them also use the cloud. The cloud can be used to augment classic on-prem enterprise deployments with cloud platform as a service features. The cloud can also be used as a reliable way to scale during high load events. Today, a common architectural pattern is to have your application broken up into services. Each of those services has multiple instances. When the load on a particular service is under lots of demand, you create more instances to handle the increased load. How do you monitor the load on each service? How do you know when to spin up new instances of that service? Load analysis and load balancing across different services can be implemented by placing agents throughout your infrastructure. These agents gather data about services and service instances and route that data to a centralized place. The centralized control plane can be used to make decisions about load balancing and traffic routing. Ranga Rajagopalan worked on networking at Cisco for a decade before co-founding AVI Networks as the CTO. AVI Networks builds modern load balancing software. And in today's episode, Ranga describes the requirements of load balancing. We talked about the evolution of network infrastructure, the impact of the cloud, and the technical decisions that Ranga and his team have made when architecting AVI Networks. Full disclosure, AVI Networks is a sponsor of Software Engineering Daily. Spring Framework gives developers an environment for building cloud-native projects. On December 4th through 7th, Spring One Platform is coming to San Francisco. Spring One Platform is a conference where developers congregate to explore the latest technologies in the Spring ecosystem and beyond. Speakers at Spring One Platform include Eric Brewer, who created the CAP theorem, Vaughn Vernon, who writes extensively about domain-driven design, and many thought leaders in the Spring ecosystem. Spring One Platform is the premier conference for those who build, deploy, and run cloud-native software. Software Engineering Daily listeners can sign up with the discount code SEDaily100 and receive $100 off of a Spring One Platform conference pass, while also supporting Software Engineering Daily. I will also be at Spring One reporting on developments in the cloud-native ecosystem. I would love to see you there and have a discussion with you. Join me December 4th through 7th at the Spring One Platform conference and use discount code SEDaily100 for $100 off of your conference pass. That's SEDaily100, all one word for the promo code. Thanks to Pivotal for organizing Spring One Platform and for sponsoring Software Engineering Daily. Ranga Rajagopalan is the co-founder and CTO of AVI Networks. Ranga, welcome to Software Engineering Daily.
I'm happy to be here, Jeff.
Today we're going to talk about load balancing and some modern approaches to load balancing. Let's start with the idea of load. It's 2017. What are the different types of load that exhibit themselves on a computer system?
Load is nothing but a demand. For any system, for example, it is the amount of demand that you pose on the system. More specifically, for a computer system, there are different types of load. The number of users who are accessing the computer system is a form of load. The requests that they are posting to the system is a form of load. The amount of throughput or bandwidth that they are consuming as a result of those requests or transactions is a form of load. So these are different types of load and the demand that they pose on the system.
Mm-hmm. When a computer system is under lots of load, that system needs to distribute that load so that no single component gets overwhelmed with the traffic, with the load that results from the traffic. And this is called load balancing. What are the different parts of an application that need to be scaled or need to have load distributed across them to do this load balancing operation?
Sure. A closely tied concept to load is capacity. So capacity is the ability to meet the demand or meet the load that is posed on the system. And there are different bottlenecks in the system when there is more and more demand on the system. Let's take some examples. When you increase the number of users who are accessing the system, let us say it's a really large application and there are literally millions of users accessing that application. So now you have 1 million users logged on. Each user has been authenticated, and each user has a session associated with that specific user. So that is one form of load. Now, let's say each user actually starts interacting with the application. An application can be your Facebook app on your phone, for example. As you start interacting with your application, let us just say you're scrolling down your Facebook app. You will constantly see that it is updating notifications, it's updating pictures, it's updating videos. Each and every one of them is a request that goes back to the application, and then a response comes back from the application. And so as the number of users increase, the number of requests and responses keep increasing. So depending on the load, different parts of the system can become the bottleneck. Mm-hmm. So we need to increase capacity to meet this load. And there isn't a single server or a single storage that is capable today of literally scaling or increasing its capacity dynamically. So a common technique is we increase the capacity in the system by using multiple servers. And when we have multiple servers or multiple storage units, then we need something that will distribute the load across those multiple servers. And that is a load balancer, and that's what load balancers do.
Mm-hmm. This load balancing can take place within a single data center, or we can scale up across multiple data centers, or maybe we're a enterprise company that's been around for a while. We've got a lot of on-prem servers, and we also have a cloud. We've got a hybrid model where part of our infrastructure is on-prem, part of it's in a data center on AWS or Google or Azure. When would we want to scale into these different areas of our infrastructure? Like, how would we want to scale into the data center? Would we want to scale into our on-prem servers? Does it matter? What are our different options, and how should we choose them?
Great question. Usually, for scaling a single application, you almost always want to scale that application across multiple server and storage instances within a data center. That's how almost all applications start, and that's how they are deployed. And to do that, you front-end multiple instances of servers or storage with what is commonly called as a load balancer. Now, almost all applications today, especially enterprise class applications, or even a lot of widely used consumer applications, are also deployed across multiple data centers. There are several reasons for it. First reason is just user proximity. The network latency delay, which is just governed by the speed of light, is at least 100 milliseconds coast to coast. So that is just a huge delay users are going to see in response times if they have to reach out all the way across from East Coast to West Coast, for example. So you almost always want to serve users closer to where they are, and that means multiple geographically distributed data centers or regions if you are using a public cloud. The other reason why you want to deploy applications across multiple data centers is high availability or disaster recovery. So if one data center completely or one region completely goes down, then you still want the application to be up. You want your users to be served. So you almost always want a backup data center that will serve applications and that will serve users. And the third is just for maintenance. If you want to bring down one data center or one region for maintenance, then you have the ability now to reroute users to another data center, serve them from that data center, while your primary data center or its applications are going through maintenance.
We will come back to the question of where we should be doing our scaling. Let's talk about what we are scaling. There's the trends in application development that are changing because of cloud, because of infrastructure as a service, because of changes in programming languages. What are the important trends in application development that are changing how we want to do load balancing?
Sure. Let's take a step back. So in the beginning, all applications were client server. So that means the application was completely monolithic. There was just one blob of the application, if you will, and clients used to access the application. In the 2000s, and even until now, this sort of became slightly broken up into a few tiers where you would almost always have a front-end tier that is usually called the web tier or the presentation layer, and then the actual application logic, which is called the application tier, and then the storage or the persistence layer, which is the database tier. So this is usually known as the three-tier application in the industry. And this pattern started appearing in the early 2000s, and this is the most common pattern. I would claim over 90% of applications in use today are deployed with this pattern. But this is also changing. The presentation as well as the application tiers are now being broken down further into microservices, where each individual service performs a very specific function. And there are a few reasons for it. Primary reason for this being just agility. Imagine you make a simple change in your application in the three-tier model. And imagine running through, say, 10,000 test cases to roll the change out to make sure that you haven't broken something, right? That is just going to take a long time to make a simple change. Whereas if you have broken down the business logic into, say, 15 or 20 microservices, and now when you make a change, you only have to run, say, 500 test cases to roll that out, then you can do it a lot more often. So deploying these as microservices almost always means more agility and being able to update and roll out more changes faster. So this is a fundamental way in which application development and deployment is changing. And another trend that is also making this possible today is containers, which makes application development, packaging, and their deployment a lot better than what it was before.
We are breaking our applications up into microservices. We're putting those microservices into containers. How does that change how we want to do load balancing?
So in the traditional three-tier architecture, you still needed a load balancer in front of every tier. You would have a load balancer in front of your presentation tier that would spread the load across multiple instances of those. You would also have a load balancer in front of your business logic or application tier. And if necessary, you would have a load balancer in front of your storage or database tier. But now imagine the business logic split apart into 15 or 20 different microservices. And each one scales independently. Each one is a service which has its own high availability requirements independently. So what you really need is a load balancer in front of every one of those microservices. So where you needed a single load balancer in front of your application tier, you need 15 or 20 load balancers in front of your microservice or set of microservices. And this not just increases the number of load balancers you need, it also changes how your load balancers are deployed, because it is no longer feasible or possible to have monolithic load balancers where all the traffic is routed through that single choke point, so it is able to load balance. But now you have to have 15 or 20 different load balancers that are deployed closer to where the microservices are running in a distributed way.
You are programming a new service for your users, or you are hacking on a side project. Whatever you're building, you need to send email. And for sending email, developers use SendGrid. SendGrid is the API for email, trusted by developers. Send transactional emails through the SendGrid API. Build marketing campaigns with a beautiful interface for crafting the perfect email. SendGrid is trusted by Uber, Airbnb, and Spotify, but anyone can start for free and send 40,000 emails in their first month. After the first month, you can send 100 emails per day for free. Just go to sendgrid.com/sedaily to get started. Your email is important. Make sure it gets delivered properly with SendGrid, a leading email platform. Get started with 40,000 emails your first month at sendgrid.com/sedaily. That's sendgrid.com/sedaily. This load balancing that takes place, it's easy to imagine we want to scale up an application and we're going to scale it up. We're going to do something to scale it up. But we actually need to get data about how our overall application architecture, how that application's health is performing. So we actually need to have some kind of monitoring in place to be able to respond to changes in the environment, because changes in the environment are detected by changes in the monitoring. What are the methods for gathering application health data? And then what are the indications that health data is saying, okay, we're going to need to do something to scale. We're going to need to do something to balance our load.
Right. Great question. So in the traditional way, when load balancers were first deployed, we have established a need for load balancing. That is, we need to scale applications, and the only way to scale them is by deploying multiple instances of that function. But what we have not discussed is how do you determine how many instances you need? That is, how do you determine how much capacity you need? So this has been very static traditionally, which essentially means the operator would be monitoring the metrics that correspond to load, which often can be the number of users, the number of connections from those users, the number of requests going through the system, the bandwidth or throughput through the system, the number of transactions those users are making. So these are the common metrics that the administrator would be monitoring. And because it's a human, they would be monitoring macro trends. They would be monitoring, for example, what is it this week, or what is it this month, and so on. And then they would be monitoring it in a more coarse way and increase capacity for applications if they see an upward trend, or decrease capacity if they see a downward trend. But because this happens by humans, it is quite infrequent. And this also means there's a lot of wasted capacity, because you have to account for changes that happen, for example, within a week, within a month, or sometimes even within a day. And so you have to have capacity that would make the peak capacity, for example, every month, or the peak capacity every quarter, and so on. So that meant a lot of wastage. That meant a lot of stranded capacity. Now, so the metrics you still monitor in a modern infrastructure are still the same, except the difference is it is going to be just in time. The difference is going to be the difference between, for example, car that you have parked in your garage, which is there whether you need it or not, versus Uber that you rent out exactly when you need it, and when you don't need it, you don't own that piece of infrastructure.
Mm-hmm. As we're gathering this monitoring data and understanding how the health of our application trends, we might notice that, hey, every afternoon we get a huge traffic spike at 4:00. And with that in mind, we don't necessarily need to have our load balancing scaling in response to that demand spike. We could learn to scale in advance of that spike. Or if we know we're going to have fewer customers at a certain time, maybe we can scale down our capacity. What are some good strategies for this predictable scalability, for this predictable load balancing?
Exactly. So step one is moving from a static, coarsely monitored environment where a human monitors this and then decides by manual action to increase or decrease capacity, to a more automated deployment model where the load balancer itself monitors load versus available capacity, and then take some actions to dynamically increase or decrease capacity of the application. The next step in that evolution is learning the pattern of load on the application using machine learning techniques. Almost all applications follow a pattern that is based on either time of the day or day of the week, or sometimes even specific times of the month, and so on and so forth. Once you learn the pattern of an application, then the algorithm can adapt itself to always keep capacity ahead of the load. So, for example, if it's a business application that starts peaking at 8 a.m. and the load starts going down at, say, 5 p.m., then you can bring more capacity online, say, at 7:30 a.m. So there is sufficient capacity available by 8 a.m. And then you can bring down the excess capacity, let's say, by 6 p.m. in the evening. So these are some techniques that you can do based on learned pattern of load on applications. And this makes it very efficient in terms of how you actually spend your costs for that application.
Mm-hmm. You worked at Cisco for many years, I think a decade or something like a decade. And you saw the infrastructure management changes that came with the cloud. You saw the before and after. And we're going to get into a discussion of how enterprises do load balancing. But first, I want to understand how, because there's a lot of enterprises that were around both before and after the cloud. And you have probably seen as much as anybody else how those enterprises have changed their infrastructure over time. What are some of the infrastructure challenges back then that, when you were starting your career at Cisco or in the early years of your career, what are the infrastructure challenges back then that newer programmers today take for granted that we don't have to do at all?
Sure. Yeah. Now, programmers or developers almost always want some things from the infrastructure. So traditionally, it's servers, it can be storage, it can be access to services like load balancing or security like firewall and so on and so forth. Especially, I would say, in the mid-2000s, when you needed more compute capacity, for example, you'd have to open an IT ticket, and pretty much all servers at that time, you'd still have to buy hardware. So that meant typically weeks of lead time when IT actually ordered it, racked it, stacked it, and then you would have those servers. So that meant delay. So that meant you had to forecast and you had to be accurate in your forecast. The budget had to be approved and you had to buy and deploy the servers. And so that was the situation. Virtualization changed that somewhat. So now you are able to break up your monolithic servers into smaller pieces. That meant you could give out virtual machines to developers quicker, but still it would mean days of waiting instead of weeks, because you would still have to open a ticket and someone had to get to it and create a VM, make sure it had the right connections and everything, and then make that VM available. That changed then into a self-service model, which is what we see today with the cloud, where there is no one in between the developer and the infrastructure. The developer goes to a console or uses an API to get access to compute. It can be storage. It can also be network resources, whether it is connectivity, it's a subnet, or it's load balancing, or it's security, including firewall rules. So that fundamentally changed how soon or how fast developers had access to infrastructure, which made everything much faster, of course.
Mm-hmm. As we said earlier, these large enterprises that in the past had to do the procurement process of racking and stacking their servers that they ordered, today they have access to the cloud, but they haven't moved their entire infrastructure into the cloud. There are many large enterprises who are still just getting started with the cloud. In this kind of hybrid deployment where they have on-prem and cloud resources, what are some of the infrastructure management challenges that these enterprises encounter?
So enterprises face a few challenges with this cloud model. So first challenge is the ability to migrate their applications from data center to the cloud. This is a non-trivial problem, and it is non-trivial because most applications are still deployed as virtual machines with their own packages and dependencies across package versions, security requirements, and so on and so forth. So they often have rules that have hard-coded IP addresses in them. So migrating them to the cloud often is a non-trivial task. The second one is, of course, all enterprises are justifiably worried about security and just to understand the right security models and security postures, compliance and audit for deploying applications across hybrid cloud is taking a lot more time. And thirdly, newer applications that are being built even as we speak today are actually the best fit for the cloud. And those are often moving a lot faster than traditional applications that are being deployed in the cloud. So what we have now is we have a situation where there will be multiple data centers and public cloud regions that have to be managed within the same enterprise for the foreseeable future. And we have a pattern where a lot of newer applications and newer deployments are being deployed in the public cloud. A lot of the applications are slowly migrating to the public cloud. Things like development and testing are moving to the public cloud. but you also have a substantial portion of the more traditional applications and applications in production that are still running within the data center. And I suspect that will continue to be the case for many years, if not a decade or more.
Your company, AVI Networks, builds elastic load balancing technology that suits the needs of the type of enterprise that we're talking about. Describe what your product does.
We have built a next generation load balancer. What I mean by that is, as the cloud architectures have evolved from more hardware-centric and individually managed architectures to more software-centric, elastic, and centrally managed architectures. As clustering has evolved from more individually managed clusters to centrally managed and centrally available clusters. Similar to that, we have built a centrally managed load balancing or service fabric that works across the cluster today. It's all software, and you really go to a single instance or a web page to access this service, and everything else happens by that controller or by that master process, including providing the service, dealing with high availability, deploying this, whether in your data center or across public cloud. So all of this is centrally managed, and it's also fully elastic because it's software, and we are able to scale the capacity available depending on the load that's put on the system.
Mm-hmm. And how does that change my workflow as somebody who's leading an engineering company, that I have this new load balancing technology where I have a centralized control plane and I can, set up load balancing rules and whatnot? What exactly changes about my workflow?
Yeah. A few things change in a fundamental way. So instead of an army of operators who have giant spreadsheets where they manage a fleet of hundreds of load balancers, you really have one place to manage all your load balancers. And that is a huge advantage in terms of just operations and not making mistakes and so on and so forth. Second one is, sorry.
No, go ahead.
Second one is elasticity and scale. So because it's software, it's completely elastic. So that means it only uses as much capacity as you really need, and it dynamically scales the available capacity as you need it. A third is it completely unlocks different application architectures. So previously, with a monolithic load balancer was a good fit for more traditional three-tier architectures where traffic naturally flowed through a choke point or choke points in the system where you could perform load balancing. But now, with applications disintegrating into microservices, you also need to disintegrate the load balancer into more distributed services, or service proxy or service mesh, as we call it. And this is only possible if you fundamentally rethink the architecture into a more cloud-like architecture. So those are few ways in which the AVI load balancing platform changes how you use, deploy, and consume load balancing.
Simplify continuous delivery with GoCD, the on-premise, open-source, continuous delivery tool by ThoughtWorks. With GoCD, you can easily model complex deployment workflows using pipelines and visualize them end-to-end with the value stream map. You get complete visibility into and control over your company's deployments. At gocd.org/sedaily, find out how to bring continuous delivery to your teams. Say goodbye to deployment panic and hello to consistent, predictable deliveries. Visit gocd.org/sedaily to learn more about GoCD. Commercial support and enterprise add-ons, including disaster recovery, are available. Thanks to GoCD for being a continued sponsor of Software Engineering Daily. Let's talk about how this is implemented. You have these agents that are sitting in every service because we're going to want to scale the different microservices in our application based on certain rules that we're going to set or certain schedules that we're going to want to set. So you've got agents that are sitting alongside every microservice, and then the agents are communicating with a central control plane. Describe that architecture in a little more detail.
Yeah, that's exactly how it works, Jeff. So there is a central control or management plane, and that is the API endpoint. What I mean by that is where you actually create the service. And dynamically, the central control plane creates agents or proxies as many as you need for every microservice running in your environment. And it's the controller's responsibility to manage the lifecycle of these agents or proxies. So it creates them, it destroys them, it monitors them, it upgrades them, it scales them out as necessary. And when you create a service in the AVI system corresponding to a microservice, the controller is responsible, for example, for allocating an IP address for that service. It's responsible for mapping that IP address to a DNS or a domain name entry. And is also responsible for pushing that policy out to the agent, which actually performs the load balancing function. So the actual work of performing the load balancing, the data plane, if you will, is the agent or the proxy. The controller is primarily the brains of the system. It's responsible for creating these and managing these agents and pushing down the policies or the service configuration information to these agents.
We've done shows about a service mesh. There are some open source projects around a service mesh like Istio and Linkerd, where every service gets a sidecar container, and the sidecar container monitors and aggregates the data that's in the service instance, and that can help with load balancing. That can, it's just kind of an open source model that sounds somewhat similar to this, but it's probably a little less managed, and there's probably some other differences. How similar is that approach? Because I think that's kind of a pattern. That's maybe the sidecar pattern or whatever you want to call it. How similar is that to what you do with AVI?
Exactly. Service mesh is a term that really just means that the set of services you need, like load balancing, are deployed in a distributed way or in the form of a mesh or a fabric in your system. Now, there are 2 or 3 patterns on how you can actually deploy and use a service mesh. The first architecture or pattern or deployment is as you described, which is every instance of a microservice has an associated sidecar or a proxy or an agent with it. So this is the most granular approach of how you deploy these proxies in a service mesh. One step below in terms of granularity or above in terms of coarseness is if you have a proxy per microservice. So if you think about a traditional 3-tier application, which typically has the presentation, application, and database tier, and you break up the application tier into, say, 15 or 20 different microservices, and each microservice, let's say, has 10 instances running in it. With the sidecar model, you would take, let's say you have 20 microservices with 10 instances each, that's 200 instances. So you would have 200 sidecars associated with every instance of the microservice. With a per microservice model, you would have 20 instances of proxy, with each proxy serving a microservice. And all of these ultimately run on nodes, whether those nodes are actually VMs or virtual machines, or they are actually physical bare metal hosts. There is also a third model where a proxy is deployed on every node. So this is a per node model. Say if these 20 microservices are deployed across 5 nodes, then you will have 5 proxies. So these are sort of 3 different deployment models of a service proxy. And like everything else, there are trade-offs and advantages and disadvantages in terms of scale, performance, security, cost, and so on and so forth.
The model that you have, where you have these agents deployed on every service and you have the centralized control plane, it seems like you could do more than load balancing. You can build other services that are supporting features that you would want in a sidecar. Are there some other things that you're building other than load balancing that you can get out of having this sidecar agent?
Yeah. So we actually support 2 models. We support a model where there is a proxy per microservice or agent per microservice. We also support a model where there's a proxy or an agent on every node.
I see.
Yeah. And the set of functions that we provide are load balancing, and then what is called as service discovery, where every microservice is associated with a name, typically via DNS. We also support a set of security functions that includes things like, for example, very simple blacklist, whitelist on who is allowed to talk to which service, to all the way to a layer 7, what is called as a web application firewall, where you're doing threat prevention against attacks on HTTP requests and responses and so on and so forth. We also do other things like authentication, where the authentication function is offloaded from the application into the proxy. And then other things associated with CI/CD, where you want to deploy an application using a blue-green deployment pattern, where you want to auto-scale applications, which we spoke about briefly earlier. So we provide a comprehensive set of services that you need for your application deployment. And we today do that in all deployment form factors, whether it's a bare metal, whether it is a virtual machine, it's a container, and whether it is a data center or in the public cloud as well.
I'm glad you caught my confusion there, because I was a little bit confused as to whether you deployed a per service agent or a per node agent. And just so people know the difference, because I think this is important, let's say I have my purchase item service that processes purchases for any user. And if I'm running a huge e-commerce site, then I'm going to want to spin up maybe 50 instances so that I can process, so I can have 50 nodes that are processing all of the purchases that are coming through my system. I could have a single agent that manages and monitors all 50 of my purchase item nodes, or I could have 50 agents. I could have one on each service purchase item service node to more closely monitor them. How should I choose between those 2 models?
Right, that's a great question. So the typical deployment pattern is that you have a cluster of nodes, and that cluster depends on what kind of workload you want to run in the cluster. They vary anywhere from, say, 10 to 20 nodes to a few hundred nodes, say 500 or 1,000 nodes. And each node typically has compute and memory associated with it. Again, anywhere, say, 8 to 16 or even 32 cores, and anywhere from, say, 32 gigs of RAM all the way to 128 gigs of RAM, and so on and so forth. And then you usually want to manage this cluster just like we manage load balancers centrally. So you would create microservices on some central orchestration system. Say you would create a purchasing microservice. And when you create that, you would say, I need 20 instances or 50 instances of this purchasing microservice. And so the orchestration system now would spin up 20 or 50 containers and schedule those containers across these. Let's say you have a 100 node cluster across these 100 nodes. And you'd also say each instance of this needs, let's say, 1 core and 4 gigs of RAM. So now the orchestration system is also doing resource management. It says, okay, so on node 1, I'm running 1 instance of the container. So if I have 8 cores, I've already consumed 1 core, I have 7 cores left. So when you create an ordering microservice, now it also schedules that across the cluster. So this orchestration system performs resource management, scheduling, and management of all the microservices and the compute resources and memory resources on this cluster. So typically, you have 2 deployment patterns or 3 deployment patterns like we spoke about earlier. So one deployment pattern is every node, let's say you have 100 nodes, every node is running 1 copy of this proxy or an agent. And in this deployment model, you'll have 100 proxies running in the system, and every proxy will be responsible for servicing all the containers running on that node. Second model is you deploy a proxy for every microservice running in this cluster. So with that, if you had 20 microservices or 50 microservices, you would have 50 agents or proxies running in them. Third model is the sidecar model, where every instance will have its own copy of proxy. Now, the trade-offs vary and are different. So in the first model, where every node is running a proxy, you would usually have the fewest number of proxies running there. So that means it is more efficient in terms of how it utilizes the resources, and also in terms of how to scale the number of proxies that are running in the system. What you lose here is, of course, the sharing, because every node is running 1 copy. That means if you have 10 containers on that, they are sharing the resources made available to that proxy. In the second model, where every microservice has its own proxy, the trade-off there is that every microservice has access to its own proxy, and it is also, the scale will be under control, because usually the number of microservices will be a much smaller number than the number of instances. But the trade-off there is that all the instances of the microservice share the performance of that proxy. And the third model is where every instance has its own proxy. Now, this is going to be a scaling problem, because if you have really large clusters with, let's say, thousands or tens of thousands of containers, suddenly you have tens of thousands of proxies. But on the other hand, because you have a proxy per node, there is little or no sharing here. And so every instance has access to resources of that instance completely. So these are fundamental sort of architectural trade-offs that you need to keep in mind.
There's a great explanation of proxying and some of these different decisions we could make. I want to shift the conversation to talking about building AVI networks. This seems like a very challenging product to build. And one of the things that stands out to me as a challenge is the different platforms that you could potentially be deploying to. So you've got private clouds, public clouds, bare metal, VMs, containers, Kubernetes, Mesos. What are the strategies for maintaining compatibility with such a wide range of potential deployment targets?
Yeah, that's a great question. So early on, when we actually architected and built the AVI product, we sort of had in mind, and we knew that this has to be architected in such a way that it will run across different deployment methods, it will run across different types of infrastructure, and it will have to serve different types of applications. So one of the key aspects of design when you have to do that is abstraction. So let me give you an example. So when the AVI software runs in a VMware cloud, for example, then it needs to talk to vSphere to create a VM. It needs to talk to vSphere to attach a network to a VM. It needs to talk to vSphere to detach a network from a VM. And the set of APIs that it uses for vSphere is specific to vSphere. Similarly, when it runs in AWS, it needs to do similar functions, but use AWS's own APIs and its own clients and so on and so forth. So an abstraction is very important. So the rest of the system should not change regardless of where the software is running. So we abstracted that out with a piece, what we call internally as a cloud connector. So what it does is it provides a set of functions or APIs. It's a microservice. It provides a set of functions and APIs internally to the rest of the system that they access to create a VM, to attach a network, to scale out and do other things. But then it uses the right set of APIs depending on what the environment is and where it's running to actually effect that change in that environment. So abstractions like these have served us really well in making sure that the fundamental software works the same way, regardless of what environment it's running, what form factor it's running on, VM, container, bare metal, or what application it's actually serving.
Tell me about another big engineering challenge that you've had building AVI Networks.
The biggest challenge, like almost all other, I think, Valley companies, is really attracting good talent. The competition for talent has been quite fierce. So we have some advantages because we are a startup, and naturally engineers want to work in smaller companies because they get to learn a lot. They get to build things from scratch, and also you can move faster and you can really advance your career faster as the company grows, and so on and so forth. So those are some natural advantages. But we're also competing for talent with a lot of other extremely well-funded startups. So that is one challenge that we have constantly faced and we continue to face. The second one right now that we're facing is just scaling the company. So we're going through a huge spurt of growth right now. We are hiring and expanding the company in all functions: engineering, sales, marketing, support, QA, everything. So again, scaling the company, bringing all the new employees up to speed and in sync with the rest of the company and making them wholly productive, again, is one of the challenges that all high growth companies go through, and we are also going through that right now.
That's funny because none of those sound immediately like technical engineering problems. Those are more like human and cultural issues.
Absolutely. I think fundamentally, I've always found that it's people and employees who solve problems. So the best people we can find and we can hire, and they will figure out ways to solve any technical problem. So finding good people and hiring them and retaining them is almost always the number one challenge I've seen in successful companies.
Mm-hmm. Tell me about the sales and the integration process when you're working with a large enterprise, because I think there's probably some people in the audience who are building software that they're trying to sell into large enterprises. They're trying to connect with a large enterprise. They're trying to figure out the best way to negotiate what is the integration process and the pricing process. Do you have any tips for that sales and deployment process?
The two ways I've seen this successfully sold into large enterprises, either the technology finds its way through developers, where developers find this new piece of technology that they like, they use. So that implies that it is readily available, it's easy to use, and developers know of them. And it works, of course. So that's one way I've seen technologies being successful in large enterprises. The other way is the more traditional route through an enterprise sales organization. In that case, almost always when it's a new product or a new technology, you have to find a champion who believes in it within the large enterprise. And then you need to work with the champion, be extremely responsive, listen to him or her, and make whatever changes are necessary, and then enable that champion to be successful within the larger organization. And these are the two fundamental patterns that I've seen when young tech companies like ours are successful with large enterprises.
What's the big vision for the company?
So we sit at this critical juncture between applications and the actual users of these applications. And we provide this set of functions that are extremely strategic. Load balancing is one of them. Security is the other one. Visibility and analytics is the third one. So we are sitting almost at this nexus of functions that are today served by at least three different markets, which is the traditional load balancer or ADC market, the security market, and then the performance management or the application or network performance management market. And so we have a fundamentally modern architecture that makes providing these functions very efficient and elastic and also easy to consume. So in the long term, our vision is to provide all these functions using our architecture and make them work in a seamless way across all the enterprise customers' environment. So that is really our long-term vision.
Ranga, it's been great having you on Software Engineering Daily. I really enjoyed the conversation.
Absolutely. Thanks, Jeff. Thanks for the opportunity of being here, and talk to you later.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!